What's time? Is it time to start? All right. Hello, everyone. Welcome to the seminar. This is Attila from the Centre of Research in Maths, and he's going to talk about. I was saying this to Glenn before. It's kind of like Holonomy. Anyway.
I already started recording, so great. Okay, thank you very much. So this is a joint work with Christopher Nehaniv, who was my former PhD supervisor, and he is still in the UK. And we have this European project called Biomix, and that allows me to fly there like twice per year and work on this automata theory stuff. So this is basically a summary of our recent understanding of the main algorithm which we use for decomposing computational structures. Okay, so starting with something very simple. So everyone knows the fundamental theory of theorem of arithmetic, that for any number, any integer, any positive integer, we can come up with a prime decomposition. And but this idea is so nice that we try to do it everywhere in mathematics. Okay, so the idea of having something composite complex and you find the indivisible building blocks is so nice that we try to follow the same pattern. So I'm not going to talk about arithmetic, but I'm going to talk about finite-state automata. But since we are more algebraic here, I will talk about transformation semigroups. So, but I still have to build up the actual structure I'm talking about. And the building block of the transformation semigroup, of course, an individual transformation, which is just a function from a set to itself. And well, I've shown this many times, but let's just do it once more. There's a very nice diagrammatic representation when I take two copies of the set X represented by dots, and I just denote it by an arrow that point 1 goes to point 3. And you can see this is transformation F, and you can see the formal representation with the two-line notation of this transformation. Okay, so I will call this set X the state set, but I will repeat this often. Okay, well, we are talking about algebraic structure, so when we have the set of transformations, of course, we want to have some operation. And our operation here is just the combination of these transformations as function composition. And diagrammatically, it looks like just stacking these images and following the connected lines. And then, of course, you simplify it and you get a new transformation. And one thing I would like to mention, the property of an individual transformation is the image set of the transformation. And there you can see that the image set of transformation F is just a set 3 and 5, while the image set of G is the 1, 2, 3, and 5. And the image set of the combined transformation is 1 and 5. And I use the action. I use exponential notation for the action on the state set, which is slightly unusual in automata theory, but I'm getting more and more influenced with the algebraic literature, so that's why the change. Okay, but we are of course not interested in just combining two, but we are interested in collections of transformations that are closed under this function composition. And here's one simple example, but a very important one. And that's the so-called flip-flop automaton, which is capable of storing 1 bit. It's like the algebraic implementation of the 1-bit memory. And basically, it consists of 3 elements. We can right, we have the right 0. So no matter which state you were, you go to 0. Okay, there is a slight notation problem, because when we talk about bits, we talk about zeros and ones, and when we talk about states, we start with 1, 2. But that's just a minor issue. And the identity operation is basically the read operation. So essentially, transformation semigroups for us, finite state automata, we don't care about at this level of the language recognition for which automata are mostly used. We just consider the state transition structure. Okay, here's another example. It's a finite counter. And well, if you come from group theory, then you recognize this is just Z3, the cyclic group of order 3. But if you consider it as an automaton, you draw this state transition diagram, and you talk about input symbols and states. And if you happen to be in state 0 and you receive input symbol +1, while you go to state 1. And of course, here we have the diagram notation as well. But of course, permutation groups are transformation semigroups, so this is just another example of those. Okay, so here is the basic idea, the main metaphor here, that we would like to do the same prime decomposition for finite state automata or finite transformation semigroups, and it makes sense to review this analogy. And of course, for natural numbers, you have the building blocks, those are primes, and for finite state automata, well, we've just seen the examples of basic building blocks, because all you need the permutation automata, so all those transformation semigroups that are actually that consist of permutations. But since transformation semigroups are not just groups, you need a destructive operation, and that's the destructive storing of one-bit information. So you need the flip-flop as well. So you have two kinds of basic building blocks. And if you know group theory, of course, you want to go for the simple groups, not just any groups. For the natural numbers, you just multiply the numbers together. While for finite state automata, you need to use quite elaborate algebraic constructions called the cascade product, or with other name you may be more familiar with, it's the Reith product, substructures of the Reith product. And for natural numbers, you get precisely the same thing. If you find the components and you put the components back together, you get exactly the same number back. That's not true for transformation semigroups. Usually you build something bigger which is capable of emulating your original structure. And the most important thing that while the prime decomposition for integers is unique up to the order of the components, for transformation semigroups you get different decompositions. And that's the key idea, because we claim that the reason why we are doing these decompositions, that they are sort of a form of understanding the underlying semigroup structure. So of course there should be more than one way to understand the same complex structure. Okay, so for computer algebra implementations, we use the so-called Holonomy Decomposition that does this decomposition for finite state automata, and I'm going to talk about this method. Okay, and so this is quite a long story. For me, it took at least how many? Let's say 11 years to understand it, and I claim that, well, probably I can now explain it within an hour. But the lesson we learned that you can prove the theorem, you can write down a constructive theorem and correct one, no problem, and you still fully understand what's going on. And I wrote a computational implementation which correctly calculated the decomposition and still had no deep understanding of what's going on. But now I think we are getting closer to that. So instead of just jumping into the details, I would like to first do the philosophy of the method and talk about abstract ideas, then show it that how it is done in the actual method. So I will talk about these three big ideas: the idea of approximation, compression, and the hierarchical structure. So what do I mean by approximation? Well, this should be a familiar concept. While you have some system and you use a sequence of simpler systems which is can gradually getting closer and closer to the original system. And the examples could be, well, you can have a curve and you can approximate it by straight line segments or Riemann sums in integral calculus. Or outside mathematics, while you can have a geographic map and zooming in shows more and more details, so you get closer and closer to the original system, which is the Earth itself. Okay, so that's one idea. The other idea is compression. So when you have a complex system and you identify some components and you find that, well, some of the components, they are of the same shape or they follow the same pattern, well, you don't have to store everything. Again, you just say that, oh, okay, I found this pattern, this subsystem here, here, and here. Okay, so you just store the pattern and the locations. And example, well, if you build a tower house and all the units look the same, well, you don't have to talk about each individual bathtub. You just say that, well, the bathtub on unit 4 and level 6, and you know exactly which needs fixing them. Another example, coming from group theory, if you happen to know group theory, is that you have the subgroups and the concept representatives. It's basically you have a subgroup and you find that while the whole group is just built of sort of copies of the same element, sort of translates. And you can also mention fractals that have the property of cell similarity. You have the same pattern applied at many levels. That's why fractals are so compressible. You just have a simple formula and you build amazing structures. Okay, and the third idea is the hierarchical structure. And it just says that control information goes in one direction only. And we need that because this makes the system simpler. And one example is the robotic arm. But since we have no robots around, so I can use my natural arm. And the idea is that, well, okay, I have 3 degrees of freedom, but whatever I do here will influence the location of my fingers, okay? So this is the top level of the hierarchy. Control information goes one way. If I just move my palm, this will not change, okay? So control information here will not go back there. And when you do addition in arithmetic, you use another hierarchical structure, and the control information is the carry. Okay, it goes one way. If you add together the digit and position of thousands, will not influence the position of ones. So it's a bit funny because the ones are the top of the hierarchy, so they can influence any other digit, but the big numbers are really the bottom of the hierarchy. Okay, so much about philosophical ideas. Here's the statement. In the holonomy decomposition of finite transformation semigroups, we approximate states and transformations of your original semigroup, and we compress this approximation data, and we put the encoded compressed form into a hierarchical structure. So now we are going a bit more into the details. So, as I said, we have a transformation semigroup acting a set of states, which in mathematics just called set of points, but the canonical representation, we just use the integer numbers. But okay, here we are a bit formal, so we are asking that, well, if given a state from the state set, how can I approximate it? And okay, let's just think about it. This is a system which can have n different states, and it is in one state, but okay, I don't know exactly in which state the system is in, but if I can say that, oh, okay, maybe it's in x1 and x4, so that's an approximation of the actual state. Or if I'm a bit more vague, I can say that, well, x1, x2, x3 is an approximation of the state x1. Okay, it's sort of an missing knowledge, being a bit uncertain. And then the extreme case, you can say that, well, the whole state set is an approximation of an individual state, when I really don't know anything about the system. So, if you accept that we can approximate states by subsets of the state set, then we have to approximate transformations by acting on subsets. And that's easy, that's very standard construction. Well, how can you transform a subset of the state set? Well, you just take all the elements in it and calculate their images. So here's an example, well, actually two. You take this transformation T, and as you can see, when you apply it to set 2 and 4, well, you get another two elements set 1, 3, but if you apply to set 1, 2, you get a singleton set. Of course, we are doing semigroup theory, so we do irreversible operations and actions as well. Okay. So now we are going a little bit more deep into the technical details of Holonomy decomposition. So we have the philosophical idea, and now we have the general idea of approximating states by a set of states. But how do we get a smaller transformation semigroup inside the bigger transformation semigroup? And well, we take a subset of the state set, and we check how the semigroup acts on that subset. Okay, and that's again a very basic notion from computer algebra and well, abstract algebra in general. That's the stabilizer. That is the set of semigroup elements that fix a subset. And now, what we do, well, that's just one set. So what is the action here? Well, we have to tile this set. And I put that roof tiling because if you think bathroom tiles, you get the wrong picture. I will show it why. Let's just go there. But I have to introduce a running example first, and that's called the Beck's automaton. And this is specially crafted for showing many interesting properties. And the reason why it's called Beck's, because when we constructed this, we were sitting in a restaurant and we were looking for a name, and there was a glass of beer on the table, and it happened to be Beck's. So we are not receiving any funding from the beer company, but the name stuck. Okay, so here we have a transformation semigroup on state 6 points generated by these 6 transformations A, B, C, D, and F. And the automaton looks like this. In the rest of the talk, we are just going to explore the structure of this automaton. And as you can see, while you look at it, can you say anything about it? Well, not really. I mean, everything is encoded in this picture, the state transition graph of the automaton, but that's not readily consumable, at least by humans. Okay, so here we have the the tiling picture of the automaton of this transformation semigroup, and this diagram became infamous in the last 10 years because we've been showing it to many people, and without a full explanation, well, people got a bit frustrated, and it's just, okay, what does it mean? And it's, oh, I have to explain everything, and that's what I'm doing now, explaining everything. But at the moment, you just have to look at the tiles of the sets. For example, where we have the state set containing all 6 elements, and it is tiled by 2 subsets, 4, 5, 6, and 1, 2, 3, 4. So meaning that when we are looking for smaller transformation semigroups, the building blocks of the transformation semigroups, we will look for the stabilizers acting on these tiles. So on the top level, we will have 2 states. If you look at this, you can find another component 1, 2, 3, 4 associated to the subset 1, 2, 3, 4, and you will find that each tile set consists of 4 tiles. Okay, it's here. And of course, as I said, the tiles may overlap. Okay, and strange enough, but on these 4 points, you have Z3 acting. So that's one component. Okay, let's see. What's the next step? Okay, so at this point, we know how to find a small component inside the transformation semigroup. You just pick a subset of the state set, see how the semigroup acts on, look for especially the ones that fix the subset, and then you can construct the component by checking how it acts on the tiling. But of course, we want to find all components, and as I said, we are doing approximation, at least in 2 different ways. And the other way of approximating is that, well, we have subset chains. Okay, so the previously mentioned approximation is just a one-step approximation, but of course you can have nested sets, and that's a gradual way of doing these. And here are just a few examples of these chains. So what happens in the Holonomy decomposition, that basically the big picture is that we act on these chains of subsets. Actually, these will be tile chains. And here's an example. It's a bit clumsy, but here we have a subset chain which can be a tile chain. Probably I forgot to mention that being a tile is meaning that it's a maximal subset, which is quite a crucial information, but I don't remember mentioning it. Okay, so yeah, when you tile, you take the maximal subsets of your set, and yeah, those are the tiles. Otherwise, tiling would be really arbitrary, and you could do the tiling with the singleton set very easily. So as you can see, we have this transformation T, and we act on this chain, and we get a lot shorter chain. And that's exactly sort of source of the problems inside the Holonomy decomposition, that you act on a tile chain, and it may go into a chain which is not a tile chain anymore because you lose the property of being maximal. So the source of complexity, and I will talk about this at the end, comes from the fact that when you do the action, you act on tile chain, you go to a chain, and you have the freedom of choosing your dominating tile chain. Okay, so you have in order to define an action on the tile chain, you have to do this correction. Tile chain act on collapses, and you have to find a tile chain, because the tile chains will be the approximations of your original state set. So you have to have a tile chain. Okay, so again the same picture, but now I would like to draw your attention to the tile chains of 4, and there are two of them, you can come.
Attila, sorry, but I think we're missing an information here. Your tiles are not maximal subsets. Are they maximal to some subject to some condition, or?
Those are maximal subsets. Yeah, I mentioned it before. But there is a twist in the story because you don't have all subsets, but that's coming in the next moment. Okay. Well, if not, then well, ask again.
Yeah.
So we have a tile chain this way, and we have another one that way. So basically, there are two different ways of representing the original state 4 in the decomposition. Okay. So here is the thing that at this point you might say that, oh, okay, but what you are doing is not really useful because it's easy if you do automata theory and you go to the power automata, which is that you blow up your state space by taking all subsets of your state set. Well, then many things become very easy. But of course, you have combinatorial explosion, right? And so the question, do we need all subsets of the state set? And well, the good news is that in general, no, because what we need to have in order to decompose the semigroup, consider only those subsets that occur as images of the elements of the semigroup, okay? So imagine you have a semigroup which consists of only one constant map to state 1. Well, all the subsets you have to consider is the set itself and the singleton set 1, instead of 2 to the power n, which is the size of the power set. But of course, in special cases, for instance, for the full transformation semigroup, where you have all transformations, you really have to, in order to do the Holonomy decomposition, you really have to do this big set and calculate with it. There is a technical thing that it's not just the set of images, but we need the extended set of images because sometimes the semigroup may not contain the singleton sets as its images. But in order to be able to tile every set, we need those as well. So. But that's just a technical thing. Okay, so now it's the same graph again. That's the tiling picture of the Beck's automaton. And probably now I'm answering Volker's question that because you don't see all maximal sub sets of a set because we don't have all subsets of the 6-element set. So instead of 64, we have just the nodes, the number of nodes. So basically, from the computational complexity point of view, you give me a semigroup, then, oh, I would like to have the Holonomy decomposition of it. And just by looking at it, I cannot tell that whether we can calculate it or not, because just looking at the size of the semigroup or the degree of the transformation semigroup will not tell how many different subsets occur as images of the semigroup. Okay, so, well, we finished with one concept, the concept of approximation. And let's talk about compression. So, well, we have a new relation here defined on the extended set of images. And we say that P is subduction related to Q when you can transform Q by the transformation semigroup denoted by M here by the monoid because we need the identity to include P. So it's like the inclusion order, but you are allowed to cheat. So P is either a subset of Q, or you can manipulate Q somehow to contain P. Okay? And we call it subduction because it's like when you have these tectonic plates and on the Earth, and one plate goes under the other one. That's called subduction. And Christopher said that, oh, that's the wrong name, because the way we defined it, it should be surduction, because Q is sort of above. And I said, okay, fine, let's Google it. We Googled surduction, and Google said that, oh, there is no such word, but probably you are looking for seduction. And we get very colorful images and decided to stick with subduction, so that, and hence the name. But, okay, this relation, I will not go into the details, but this relation is used for putting the components into order. And more important, this is a pre-order, and so the usual thing is you make an equivalence relation out of it. When you have two subsets mutually subducing each other, that means that by the semigroup action, you can go from P to Q, and you can come back. So you don't lose point, you can go around. And if you know, okay, well, first just look at the tiling picture again. So the outer boxes, those are the equivalence classes. So if, well, 2 and 4, the set 2 and 4, and the other set 3 and 4 are in the same box, meaning that in the semigroup, you can move around. You can go to 3 and 4 from 2 and 4 and back, and you can also go to 1 and 4. And if you know computational group theory, well, then you realize that, okay, when you look for the holonomy groups, you don't have to calculate the stabilizer and see how they act on the tiles, but the standard idea is that, well, you move around in the equivalence class, and in that way you can get all the permutations of your set. And that's the classical Schreier-Sims algorithm. You are interested in the generating set of a subgroup, and you go around the coset space and you get permuted in the way, and that's why you find the generator. So in semigroup theory, we do exactly the same, because an equivalence class is a local pool of reversibility. So of course, when things are reversible, we can do group theory. And okay, so the explanation. So why is it called holonomy decomposition? And the name comes from differential geometry, and I just copied it from Wikipedia, and it says, given a smooth closed curve C on a surface M and picking any point P on that curve, the holonomy of C in M is the angle by which some vector turns as it is parallel transported along the curve C from point P all the way around back to point P. Okay, well, I sort of understand, because I understand holonomy decomposition, but I'm not doing differential geometry. But the idea is that, while you have some curves in some space, and you move around that curve, and while you are moving around, your original vectors sort of move around as well. And that's what's happening here, but instead of vectors, we are talking about, instead of transforming the vectors, we are talking about permitting a set. But that's why it got the name holonomy decomposition. Okay. One more thing. Semigroup theory is basically about groups glued together in some combinatorial structure. And the holonomy decomposition shows that exactly. Because, as I said before, that in order to find the components of the decomposition, we have to find these holonomy groups. That's not quite true, because, well, we have to find them, but that's not enough, because we also need, well, if we just put groups together, we will get another group. Somehow we have to represent the irreversible operations, and that's why we have to put this bar over the group, saying that whenever we have a holonomy group, we will augment it with the constant maps to the element of the set. So, but as you can see, it's in the holonomy decomposition, it's sort of very nicely separated. We have the reversible structures, the groups, plus the constant maps, and that's how you can move a bar. Okay, so that was the compression, except that I didn't mention exactly the compression. But if I go back to this picture, see that the equivalence class has only one label indicating the holonomy group acting on that. Because if you can move around and you have a group acting on one set, well, then the group's structure can be transferred to the other set in the equivalence class. So this is how you compress it. You don't have to store each holonomy group, you just store one, and you store the equivalence class saying that, well, you can have groups on any of these. Okay, so about the hierarchical structure. Well, I talked about this a couple of times, so I will try to do it quickly. Also, time is going, so I have to do it quickly anyway. So when we have M transformation semigroups using this automata theory motivated notation that X1 is a state set, S1 is a transformation set of transformation, a semigroup, and I have n of these, I can put them together in a hierarchical structure using these dependency functions, and that's just the most straightforward way with which you can encode one-way flow of control information. So this DI says that depending on the states above, so one is the top of the hierarchy, it will tell you what to do in a component I. Okay, well, if you can quickly graph formal descriptions of slightly complicated actions, that, well, here is the way to think about it. You act by evaluating the dependency functions. Then you do the action coordinate-wise, but let's go and be more visual. And when we have the hierarchical structure, in each level we have a state set, and the state set of the hierarchical structure will be the direct product of these state set, and those which we call coordinates can be represented by a tree. And when we have that representation and we label the branches, then in the nodes we can put local actions. These will be the building, the action of the building blocks in the decomposition. And well, here I have permutation example. Well, that's what we do in semigroup theory. We talk about that, semigroup theory is interesting, but when it goes to examples, we always do group examples for some reason, because it's a lot easier to show. So, well, okay, this is just an abstract description of a permutation cascade. So this will be one element in the decomposition, which is, well, in the composition semigroup. And it just says that if the top level state is 1 and the second level state is 2, then I should do this action, 2, 3. So a cascade tree, a permutation cascade, will encode how to act according to the dependency functions. And of course, these are semigroup elements, so we can multiply them together just by doing one after the other, although it gets tricky because the first action moves the coordinates around. But basically just doing them one after the other will tell exactly how they combine. Okay, and it is just a very simple example. And that's probably, if the last few slides were a bit steep, then probably you just need to remember this one. This is a modulo 4 counter. So it's a permutation group built from 2 copies of modulo 2 counters. So this is the top level of the hierarchy. This is the bottom level. And these are, of course, just modulo 2 counters. and the way they are put together, well, if you check the Reeve product, that's a bit bigger structure because that will be the dihedral group on 4 points. What we want to build exactly just the modulo 4 counter. So this says that the dependency function is basically the carry. If the carry is 0, well, if the top level is 0, we have a 0 digit there. But on the second level, which is the position of 2's, we have to do only the identity. If it happens to be 1 and we do the plus 1 operation, that means that the number of 1's will become 0, and then we have to do as a second level in the positions of 2's. Well, of course, then the carry goes and we have to do a plus 1 in the bottom level component. Okay, so in the computer, well, here is the Beck's automaton defined by these generators, and I'll just ask for the holonomy component of the skeleton of this Beck's automaton, and it will give me that, okay, so there are 5 hierarchical levels of this decomposition, and for example, in the top level, it just says that I basically have 2 states, meaning that, well, I have no non-trivial group acting. So I only have the identity and the constant map. So on the top level, well, answering the question, well, here is the Beck's automaton. What is it doing? But just give me a very rough picture of it. And then I can say that, well, okay, it's basically choosing between 2 states destructively, okay? So you can say that, well, on the top level, this automaton is just storing 1-bit information because it stores the information whether I took this decision or that decision. Of course, when you go deeper down, you find the details, and on the second level you have 4 states and the counter acting on them, and if you go even deeper, well, you have even the symmetry group there, and then I have 2 components at the same level. Well, I just have to, in order to construct the component for the cascade product, I have to take the direct product of those, because those are not in any dependence. So basically, holonomy decomposition aims for the shortest decomposition. So if 2 components, they never influence each other, well, they can be on the same level, because there was a decision above, meaning that, okay, in which subcomponent we are in. Okay, let's have a look. And so on the top level, we can decide that whether we will do S3 on 4, 5, 6, so that will be a subcomponent, or we do the other side and we consider 1, 2, 3 as an approximation, and we will do C, well, Z3 on that. So this is basically this tiling picture is translated into, you take the components from out from this, and you put them into a Reeve product, except that the reason why we needed the cascade product, that you don't want to build a Reeve product because that explodes combinatorially. So you want to build it precisely, and see what happens. Okay, so let's just do another decomposition. But before that, let's say, okay, I have a permutation group. What's the holonomy decomposition of that? What would be your guess? Okay. Applying all the methods. So yeah, I have a permutation group. So what is the set of images? Well, I have a state space. Yeah, it's the state space. Okay, so all I can do just technically just tile that with the singletons. And what's the action of it? Well, I just get back the same permutation group. So the holonomy decomposition method is not sensitive enough to cut the group components. So you will not get simple groups. You just identify a group component and you put it into this combinatorial structure of the semigroup. But okay, let's look at the holonomy decomposition of the full transformation semigroup. When you have all transformations of degree n, and that will embed into this holonomy decomposition, where you have a full state set and you have the symmetric group acting on it, so you have all permutations, plus you need the constant maps. Second level, you have n-1 states, and you have the symmetric group of degree n-1 acting on it, and you go down to that. Well, S2 basically Z2. So this is how we can decompose that. So this is an easy one. You don't even have to go through the whole holonomy decomposition. You can figure this out. But, and here comes the difficulty that I mentioned before. When I choose the tile chains to represent the original state, I have freedom to choose different ones, okay? And when I do the action, I act on the tile chain. While it collapses, then I find the dominating tile chain containing that. I again have freedom. And that freedom is a source of a problem, because we don't have a unique representation of the full transformation semigroup as a cascade product, but we have many. And the next step is studying this representation problem and finding the good and the minimal ones in a sense. Okay, just to recap. So we were interested in the prime decomposition of computational structures. Depending on whether you come in for algebra, you call them transformation semigroups. Or if you come from computer science, you call them finite automata, but it's the same thing. And we used three abstract ideas: approximation, compression, and hierarchical structure to do the decomposition. And of course, there are still more details on how to do it technically, but these are basically the big ideas. And the recent progress in our understanding was that an algorithm can do many things in one go. Then it's difficult to see what's going on. And what we did, we separated this business with the dominating tile chains. So previously we just had a recursive algorithm, or I apply this cascade transform and see what happens, see which state it goes to. But in the middle of that recursive algorithm, there was a choice of choosing a dominating tile chain. Now we separated it. Now we can look exactly that. Okay, I have this approximated action, and I can look exactly how many different ways I can do that. Okay, so the ultimate goals and the big picture in computational semigroup theory. Well, not long ago I talked about the minimal degree transformation representation problem, and while the basic question is what is computable with n states, and we did enumeration and classification of low degree transformation semigroups. Of course, we haven't answered the question that we have no single algorithm to find a minimal degree representation for an abstract semigroup, but that sort of is a work towards that goal. And what I talked about today is that, okay, if we know what is computable with n state, another question to answer that: how is the computation done? What's the structure of the computation? How I can decompose it? And that's the coordinatization of states and transformations. And the big problem is that finding the minimal cascade representations. And the reason why it's difficult, we don't even know what do we mean by minimal, because it's, well, in the transformation representation problem, it's a clear parameter. You just want to minimize the number of states to act on. But with the cascade ones, well, there are many things. So there could be a bigger representation, but it has some very nice properties we can exploit. We can have a nice algorithm to manipulate this coordinate system like we have in arithmetic when we do addition and multiplication together. Okay, so these are the big questions, and here's the link to the software. I didn't have time to include the logo of the software package, but it's here on my t-shirt, SGP deck, and also we have a blog on computational semigroup theory. And that's it. Thank you very much.
So, anyone got any questions?
Yeah, it's all clear. Great. I told you I can explain it in an hour.
How about in Penrith?
That was already asked mine.
No. All right. Thanks again.
Okay.